Okay, I think we can start. So good afternoon, everyone. Today we have a pleasure to attend the talk by Dr. Srijita Kundu. Srijita completed her PhD at National University of Singapore under the supervision of Rahul Jain. And since 2022, Srijita joined us, us at IQC. Joined IQC as a postdoc, and Srijita is working at quantum Curie and communication complexity, and also in cryptography.
Thanks for the introduction. Yeah, it's going to be a complexity theory and quantum talk. How many people in the audience have a background in complexity theory or quantum? Okay, cool. I'm going to try my best. Thanks for inviting me. I'm going to talk about an oracle separation between QMA and QCMA with bounded adaptivity, and this is joint work with my supervisor Shalif and David. So I'm going to define the complexity classes QMA and QCMA first. So these classes are both quantum generalizations of NP. I hope people know what NP is. So this is just like MA is a randomized generalization of NP. So these classes are described in terms of like a game between a computationally bounded verifier Arthur and like a mysterious untrusted wizard with unbounded computational power Merlin. So Arthur has some input in 0, 1 star, and he wants to know if his input Z is a yes instance of a particular problem. And Merlin knows Z, and Merlin basically wants to convince Arthur that it is a yes instance by giving him a witness. And the requirement is if the input that Merlin has, then there exists some witness so if the input is a yes instance, there exists some witness that Merlin can use to convince Arthur with high probability that it is a yes instance. And if it is a no instance, then every possible witness that Merlin sends to Arthur should be rejected with high probability. Now, how do you make this setting quantum? So in QCMA, what is done is Arthur is made a polynomial-time quantum machine. So Merlin sends Arthur a classical proof depending on the input Z. Proof, or I'm going to use proof or witness interchangeably, classical witness or proof P of Z to Merlin and to Arthur, and Arthur runs some polynomial time quantum algorithm on it and decides if it is it is a yes or no instance. And in QCMA, both Arthur and the proof in QMA both Arthur and the proof are quantum. So depending on Z, Merlin sends some quantum state psi Z to Arthur, and Arthur is still a polynomial time quantum machine. So Arthur runs some verification protocol on the quantum proof and decides if it's a yes or no instance. Okay, so first of all, it is clear that QCMA is contained in QMA because a QCMA witness can be encoded as a computational, what is called a computational basis state as a quantum state basically. So the real question is whether.
Let's just look at the base slide for 10 more seconds.
Okay.
Could you remind me what PZ is again?
It's a classical, it's a polynomial-sized classical string that depends on Z. Yeah. Okay, so the real question is whether QMA is contained in QCMA. So this is essentially asking when the verifier Arthur is already quantum, do quantum witnesses provide any advantage? In order to think of what this means for like a specific problem, we can consider a QMA complete problem. The canonical QMA complete problem is the K-local Hamiltonian problem. Essentially, this is a quantum generalization of K-sat. In the K-local Hamiltonian problem, you have an input which is a Hamiltonian on n qubits. This is, I don't want to expand too much on what a Hamiltonian is, but it's an operator basically which represents an energy function or something for physicists of these n qubits states, and it's a sum of a bunch of local terms. Each of the terms HI act on only k qubits, that's why it's called K local. And the question is to determine whether the lowest energy eigenstate of this Hamiltonian has eigenvalue at most A, or if all eigenstates of the Hamiltonian have eigenvalue at least B. So, the first one is the yes instance and the second one is the no instance. So, this problem and we are given a promise that this B did someone ask something? Oh, maybe outside. And we are given the promise that B minus A is at least 1 by poly. And if we are given this promise, this problem is in QMA actually, because you can send the lowest energy eigenstate as the quantum witness, and there is a quantum algorithm that Arthur can run if given this witness to determine if the eigenvalue is less than A. But the problem is maybe like for every k local Hamiltonian, there exists some efficient circuit that prepares the lowest energy eigenstate, which is also called the ground state. Now, if such an efficient circuit existed, then Merlin could just send Arthur the description of such a circuit, and then Arthur could prepare the circuit himself and then do whatever he was doing previously. So, Aharonov and Nave in 2004 conjectured that QMA is in fact equal to QCMA, just because like maybe at the time it seemed to them that this is in fact possible, that there is an efficient circuit that prepares the ground state for many k local Hamiltonian, although it's been 20 years since then, so maybe they changed their mind. There have been like many developments in Hamiltonian complexity theory and stuff. I'm not sure like most people believe that QMA is equal to QCMA these days. Anyway, so you have two complexity classes and you want to know if they are separate or equal. So, the first thing a complexity theorist would do is to see if they are separate or equal with respect to an oracle. So, if you can show that there is an oracle O such that relative to that oracle O, QMA is not equal to QCMA, I am going to explain what that means. Then that means that a relativizing proof technique can't prove that QMA is equal to QCMA. A relativizing proof technique means that basically whatever the proof is doing, everything would basically be fine if you gave every algorithm in the proof access to an oracle. So, usually when we talk about oracle separations, the oracle is a classical oracle. So, it is some arbitrarily hard function 0 1 star to 0 1 star. So, the function is arbitrarily hard, but we give all algorithms involved access to this oracle, so they can query the oracle at whatever input and learn the value of the function or whatever this oracle is giving in one time step. And yeah, this is usually just a classical function. But the thing is, the proof techniques that relativize with respect to classical oracle also relativize with respect to quantum oracles. By quantum algorithm, I mean, by a quantum oracle, I mean a black box unitary. So, for every n, there is a unitary un, and suppose you have a quantum algorithm, and it supplies n, and it supplies an arbitrary n qubit quantum state, and the oracle basically applies un to the state that it supplies. And as it turns out, quantum oracle separations between QMA and QCMA are in fact known. The first separation was shown by Aaronson and Kuperberg. This was the first separation between QMA and QCMA. This was in 2007, and yeah, it was definitely a very quantum oracle that they used to separate QMA and QCMA. Since then, Pfefferman and Kimmel showed a separation with respect to what they called in-place permutation oracles. So, these are like a bit less quantum, but still kind of quantum oracles. And after that, Basirian, Pfefferman and Marwaha also showed some separations with respect to another non-standard oracle model, which is still quantum. Now, see, I said there is a quantum oracle separation between QMA and QCMA. After the first one, after Aaronson and Kuperberg's result, people were still trying to get oracle separations with less and less quantum oracles. People really want to get a classical oracle separation between QMA and QCMA. Now, why is this? So, when you make the oracle quantum, you're kind of making the problem kind of quantum. you want to know if quantum witnesses provide any advantage over classical witnesses, but it's kind of more intuitive that they will provide an advantage if you're making the oracle, the problem quantum. And also classical oracle separations are separations in the standard model of query complexity, which is like a pretty simple model in which we can get unconditional separations. And the thing is that most of the quantum algorithms that we do know which provide an advantage over classical algorithms, they are in fact query algorithms. So if quantum witnesses provide any advantage over classical witnesses, we kind of expect it to happen in query complexity. So fortunately, recently there has been some progress towards a classical oracle separation between QMA and QCMA. The first work was in 2023. So Natarajan and Nirke showed an oracle separation between QMA and QCMA in the distributional oracle setting. So this means that the oracle comes from a particular distribution, and Merlin knows the distribution, but Merlin does not know which oracle from the distribution exactly it is. So this limits Merlin's power quite a bit, and that's why they are able to show a lower bound basically. And the second work which showed a classical oracle separation was by Lee, Liu, Pelikanos, and Yamakawa. LLPY maybe from now on because we'll be referencing them quite a bit. So they showed a separation between QMA and QCMA with respect to a classically accessible classical oracle. So remember, the QCMA algorithm is a quantum algorithm. So it has access to a classical oracle, but it can in principle query it in a quantum way in superposition. But in Lee, Liu, Pelikanos, and Yamakawa's model, they limited the way in which the quantum algorithm can query the classical oracle. The quantum algorithm is basically only able to query it with classical queries. And in query complexity, this basically corresponds to the setting of MA, like simple randomized Merlin Arthur. And yeah, in that setting, they are able to show a separation. Any questions so far? Oh, okay. Okay. So now I come to our result. So yeah, we show an oracle separation between QMA and QCMA in with a classical oracle that the verifier can query quantumly, but our catch is that the verifier can only query the oracle with like bounded adaptivity. So the QMA and QCMA algorithms here have oracle access to A, but they can almost make R batches of parallel queries to the oracle. And each batch can have polynomially many queries, so there are polynomially many queries overall. But yeah, there can't be too many adaptive rounds. The oracle we use is a simplified version of the construction of Lee, Liu, Pelikanos, and Yamakawa. And it makes use of this problem by Yamakawa and Zhandry, which was recently put forward by them in 2022 to show a quantum and a separation between quantum and classical algorithms with respect to a random oracle. Unfortunately, the parameters of the Yamakawa-Zhandry problem are not quite good enough, or at least we can't show that they're good enough for a general oracle separation. And we conjectured that maybe there is a problem with good enough parameters, which will lead to a full separation by our techniques. It might be the Yamakawa-Zhandry problem itself with a better analysis.
What does parallel mean there?
Huh? What?
What does parallel mean here?
So you can like, so for example, if you can decide to query the first bit and the second bit at the same time, but depending on your query out, so if you want to make adaptive queries, depending on your outcome of the first query, you decide where to make your second query. Yeah.
So parallel means you can query multiple bits at the same time?
Yeah, but if you can't make too many adaptive queries. Yeah. Okay, so I said oracle separations are basically separations in query complexity. So I'll introduce the query complexity and particularly quantum query complexity setting first. So in query complexity, we have a known function or relation that we want to compute, but the input that we want to compute this function or relation on is unknown. So, we get access to this input via an oracle. So, if the input is z, the oracle is O of z, and we can make queries like this. Suppose we query the first bit of z1, first bit of the input z, so z1, and we get the answer 0. And depending on this answer, I can, as I was saying, decide where to query next. So, suppose I query the 7th bit or something, get answer 1, and depending on this answer, I can decide the next position I am going to query, or I could also stop. Like for example, if the function I wanted to compute was or something, I have seen a 1, so I already know the value of the function. The complexity measure we are usually going to be concerned about here is the number of queries. So, everything else is free, we just want to know the number of queries. I mean in QCMA and QMA there is also going to be a witness size involved, but like in a very basic sense the complexity measure is the number of queries. And this, what this model looks like quantumly is, so you have an unitary oracle O of z. So, given so you have a query register and an answer register. So, in the query register you give the bit I that you want to query to the oracle, and the oracle gives the answer in the form of an XOR in the answer register. So, it has to be in the form of an XOR because it's the quantum oracle needs to be reversible. And the thing is you can query in superposition. So, you can send in this state summation over I, B, etc., and the oracle will act in a linear way on it. But note that this is you're querying this oracle in a quantum way, but the oracle is still like it's an oracle corresponding to a classical string. It's not like an arbitrary unitary like is what happens in the quantum oracle setting. And so this is what a quantum query algorithm in general looks like. This is a 2-adaptive quantum query algorithm. So you have some query registers and you also have some work registers. So suppose you apply k batches of parallel queries in each round. You have 2 rounds. So there are 2k queries in total. So yeah, you have k query registers and you apply k copies of the oracle O of z in it in each round. And before and after each query, you can apply some arbitrary unitaries in the query and work registers. The unitaries are basically free of cost. Like I said, we only care about the number of queries. And the unitaries are what is going to do the work of see what the query answer is and decide where to query next, etc. So the unitaries are taking care of that activity here. Okay, yeah, and after the last unitary, basically you measure some register and give an answer. Okay, now what do?
Sorry, can you just remind me? So OZ as a matrix, does it live in 2 to the n-dimensional space or something?
I mean, yeah, but you can describe its behavior.
Yeah, just confirming that with dimensions, right?
Yeah, I mean, it's a 2 to the n cross 2 to the n dimensional matrix, yes, but I mean, you can describe its behavior as just the classical string. Okay. Now, okay, what do the classes QMA and QCMA look like for in query complexity? As before, we have a known partial Boolean function, and so it has to be a Boolean function here because QMA and QCMA don't really make sense for relations, but it can be a partial function, so it doesn't have to be defined on all inputs. And yeah, as before, we have an unknown input z on which we have to compute this function. Now, what query QCMA looks like, as before, we'll have the Arthur and Merlin sort of setting. So Arthur has access to the oracle O of z, and Arthur is computationally bounded, so he can make few queries to the oracle O of z. And Merlin, remember, Merlin was computationally unbounded, so Merlin should know like fully z. So because I mean, in his free time, he could have queried the oracle and found out z because he has unlimited queries. And so in query QCMA, Merlin, who knows z, is going to send a witness P of z depending on z to Arthur, and depending on the witness, Arthur is going to make some quantum queries to O of z, and try to determine if Z is a yes instance. We have the requirements as before that if Z is a yes instance, Arthur must output 1, say, with high probability. If Z is a no instance, Arthur must output 0 with high probability. In query QMA, on the other hand, everything is the same except Merlin sends Arthur a quantum state depending on Z, and Arthur does things, Arthur makes quantum queries to O of Z depending on this witness. And the query, the measure of complexity in both these models is the number of queries plus the witness size. So, the witness size is the number of bits in the classical proof for QCMA and the number of qubits in the quantum proof for QMA. Okay, so before I get into how we prove QMA versus QCMA separation, I'm going to take a detour into quantum advice and communication complexity. So, an oracle separation between QMA and QCMA seems highly related to an oracle separation between two other classes, BQP by Q poly and BQP by poly. So, BQP by Q poly is the class of decision problems that a polynomial-time quantum algorithm can solve with polynomial-sized quantum advice, and BQP by poly is the class of decision problems polynomial-time quantum algorithms can solve with classical advice. So, witnesses are advice is a bit like witnesses in that, like, they are non-uniform, they can come from an arbitrarily powerful prover or whatever, but their advice is only allowed to depend on the input size and not the specific input. So, for every n you will have a specific advice, and advice is it's it's non-uniform, but it is always trusted. So, it is not like there is some Merlin who is trying to convince us no instances or yes instance or anything. So, unlike witnesses, we do not require that for no instances every possible advice must be rejected or anything like that. So, I say that oracle separations between QMA, QCMA and BQP by Q poly and BQP by poly are related. That's because
there exists some advice so that it's rejected.
There exists some advice such that with the advice yes instances compute to yeah. Okay. So, every time someone proves an oracle separation between QMA and QCMA, they somehow always also prove an oracle separation between BQP by Q poly and BQP by poly. So, the classical oracle separation between BQP by Q poly and BQP by poly is open, but on the other hand, unlike QMA and QCMA, there are relational versions of BQP by Q poly and BQP by poly, and these relational versions actually can be unconditionally separated, so without an oracle or anything, and this was shown last year by Aaronson, Berman and Kretschmer. So, the relational versions of these classes are called FBQP by Q poly and FBQP by poly. So, these classes are just like the corresponding decision classes, except therefore, like polynomially bounded relations. So, for each input Z, say that there are lots of possible outputs as long as the outputs are like polynomially sized, and the you are only required to output one of them. And this poses no problems for the definition of advice because advice is always trusted. Okay. So these this separation by Aaronson, Berman and Kretschmer was shown using one-way communication complexity. So, I am going to talk a little bit about how that was done. In the communication complexity setting, like in the query complexity setting, you have a known functional relation that you want to compute on unknown inputs, but the functional relation in this setting is like it has two inputs basically, and you have two spatially separated parties, Alice and Bob, who each get one of the inputs to the function, and they basically have to communicate with each other for the other part of the input in order to compute the function together. In the one-way setting, Alice is the only one who can communicate to Bob. So Alice sends a message depending on her input to Bob, and depending on the message that he gets from Alice and his own input, Bob outputs something, and the requirement is that with high probability or whatever, Bob's output should be the correct answer. And the complexity measure we care about in this setting is how many bits or qubits need to be communicated. Alice can send a message classically or quantumly, basically. And so you can separate quantum and classical communication quite a bit in communication complexity. So one such example is provided by the hidden matching problem. So in the hidden matching problem, Alice gets an input which is a function f from 0, 1 to the n to 0, 1. This can obviously be written as a string in 0, 1 to the 2 to the n. And Bob gets an input, a string in 0, 1 to the n. And the requirement is Bob has to output any string y and fy plus x for the particular x that he has gotten. So it was shown by I think Baryosef, Jairam, and Karanidis that there is no efficient classical deterministic or randomized protocol for this problem. The amount Bob has to communicate there has to be 2 to the n by 2. But on the other hand, there is a efficient one-way quantum protocol that only communicates n qubits, and it's like this state that is being sent. It's n qubits. And obviously, this only holds in the one-way setting because Bob's input is in fact n bits. If Bob could also communicate with Alice, everything could be solved with communication n. Okay, now with this one-way communication complexity separation, we can separate FBQP by poly and FBQP by Q poly. So it's going to work like this. For every n, you pick a family, some family of functions, fn. For any function family that you pick, you define the relation this way. I mean, you basically have to you have to output y and fy plus x, this hidden matching relation. And for any f, this is in FBQP by Q poly. Because the quantum advice state that you can give for this problem will just be the quantum Alice's quantum message in the one-way communication complexity setting. And so for every n, you have fixed a particular function. So the quantum advice state depends on f, but not any particular input. So it is a valid advice state. And the BQP algorithm that helps you solve this is Bob's measurement that he was carrying out in the one-way communication setting. In communication complexity, generally these measurements are not required to be efficient, but as it happens, this measurement is efficient. So it works out in the Turing machine setting as well. But on the other hand, there is a function family for which this problem is not an FBQP by Q poly. That's because if for every function family there was a family of classical advice that you could use to solve this problem, then there also would be a classical message that Alice could send to Bob in the communication complexity setting. Okay, and this gives a separation between FBQP by Q poly and FBQP by poly, but it can't give a separation between BQP by poly and BQP by Q poly, the corresponding decision classes. That's because of this relation by this theorem proved by Aaronson in 2004. So he showed that if there is a Boolean function, so Boolean function on two sets of inputs, Alice's inputs are n bits and Bob's bits are m bits, and it's in the one-way communication complexity setting, so Alice communicates to Bob. In this case, suppose there is some one-way communication complexity protocol. I'm denoting that by BQP 1 CC of f. Then there is also a deterministic protocol that computes the function with the same complexity as the quantum protocol up to a factor of m. M is Bob's input size. Now, remember, in this setting, Bob's input was exponentially smaller than Alice's input, and Bob's input size is in fact just n, and we had the quantum communication complexity was n. So, there would, if this were a decision function instead, there would also be a classical protocol of complexity n square. So, we wouldn't be able to get any separation. Does anyone have any questions for so far? Okay, I'm going to move on. Yeah.
There is a functional version of this Boolean.
Yeah, it's not total. This one is a total function, a total relation.
Is that important for you?
Yeah. Yeah, so I think you can't get, at least for a total function, you can't get a separation. For for a total function, you obviously can't get a separation because of Aronson's result, and yeah, it's total because
I mean, Scott's result, it's meaningful only because the input for one party is much shorter than the input for the other party. Right?
oh right. Also, I think sorry. Yeah, the FBQB thing maybe necessarily doesn't have to be total, but we definitely need that. That one party's input is much smaller than the other party's. Is that true for the one you're describing, the other version of hidden matching? Okay. Yeah, I guess that's why it doesn't work. Okay. So I took this whole detour because the FBQB by Q poly and FBQB by poly is separation is actually like kind of related to the QMA versus QCMA separation. In fact, the result by Lee, Liu, Pelikanos and Yamakawa, their recipe is, I mean, we are going to use a simplified version of their recipe. The construction by them was a little bit more complicated. So they gave a recipe to convert an FBQP by Q poly separation to FBQP by Q poly versus FBQP by poly separation to a query QMA versus QCMA separation. Well, they also give us way to convert an FBQP by Q poly separation, FBQP by Q poly versus FBQP by poly separation to an oracle separation of BQP by poly and BQP by Q poly, but I'm not going to talk about that part. And the recipe is not black box, so it's not going to work for any relation that separates these advice classes. Okay, but their recipe looks like this. The oracle constructions will be inspired by this BPP problem. So suppose you have to distinguish two oracles. One oracle has ones in all locations, say that is the yes oracle, versus another oracle, say the no oracle has ones in very few locations and zeros in most locations. So a BPP algorithm can do this because you just sample a random location, query it, and output whatever you see. And because it's like lots of ones versus few ones, you'll obviously succeed with high probability. The QMA versus QCMA oracle will be inspired by this, but with like much bigger oracles. So okay, we are going to use the idea with behind this BPP oracle, and we are also going to use a relation R that separates FBQP by Q poly and FBQP by poly. So as we saw with the hidden matching problem, the relation was like this: f x comma u. So f is like Alice's input in the communication setting, x is Bob's input, and u is Bob's output. And we should think of f as being much larger than x, exponentially larger. And for every f, we define R of f, which just consists of xu pairs such that fxu is an R. And it's going to be important for us later that this is a TFNP relation, every R of f. By TFNP relation, I mean that for every f and every x, there is some u such that XU is an R of F, and also that for every XU pair that is an R of F, there is a short partial assignment on F that I can tell you to convince you of this case. By this I mean, suppose you know XU is an R of F, then you definitely know some bits of F. So for the hidden matching relation, remember XU comma either 0 or 1 was in F if Fy plus x had value 0 or had value 1 accordingly. So in that case, those two bits of F are definitely revealed by you knowing that the XU pair is an R of F. Okay, but yeah, that's only going to be relevant later. So okay, suppose we have this relation R of F. Now we are going to construct our oracle like this. So the oracle is going to look like this. Each position in the oracle is going to be labeled by x comma u, where x comma u is a possible pair that is an R of F for any F. And in the yes instance, for XU, so each oracle is going to be labeled by a hidden F basically. And in the yes instance, all the XU pairs corresponding to XU that are in R of F will have value 1, and the rest of the positions are going to be 0. In the no instance, on the other hand, some of the XU pairs that were supposed to be 1 are going to be erased, and the rest are going to be 1. So it's kind of like the BPP problem. Basically, here you had lots of 1s versus very few 1s. Instead, in this construction, we are going to have like hopefully few 1s only corresponding to the positions in which XU is an R of F, versus like very few 1s where like even most of those 1s have been erased. Okay. So more formally, the oracle is going to look like this. So each oracle is going to be labeled by a hidden F, like I said, and some set E. E is a subset of the X's. So O of XU is going to be 1 if XU is an R of F, like I said, and also if X is not in the erased set E. So E is going to be a set of like erased inputs. And yeah, if XU is not an R of F, it's definitely 0. And the problem is to distinguish between E equal to empty set, the yes instance. Equal to empty set means that there is no erased set, so nothing has been erased, or most of the XUs have been erased, so E is a very large set. So yeah, the first one is the yes instance, and the second one is the no instance. Now the idea is this problem is distinguishing these two problems is in QMA, because remember we picked R of F such that there is a quantum advice that for any x lets us find an XU pair in R of F. So you can provide the quantum advice, say let's call it Z of F for R of F, as the QMA witness. Now if a BQP algorithm has this witness, well, what can it do? It can sample a uniform X, then use the advice state Z of F to find a U such that XU is an R of F. It can do this without any queries because, yeah, I mean by definition from the advice state. Now after this, it only makes a single query to the oracle O of Fe at the XU for the XU pair that it has found, and it will output the answer. So this will work with high probability because, I mean, if you have the correct advice state, then you have found an XU pair that was supposed to be in R of F, and so if you have found that the answer is 1, that means with high probability you don't have the erased oracle, or if you find the answer 0 at that location, that means with high probability you do have an oracle in which many x's were erased. Now, so we've shown that this problem is in QMA. Now what we want is that this problem should not be in QCMA. But on the other hand, I said the construction is not black box. So what we are hoping for, that this problem is not in QCMA, is actually not true if we use the hidden matching problem. So okay, if you recall, the hidden matching problem looks like this. R of f consists of x, comma y, comma the bit fy plus x. Okay. So this means that for every x and y, either x comma y comma 0 is in R of f, or x comma y comma 1 is in R of f. So this means in fact that you know, we are not in the case that we were hoping for, that in the yes instance we have like very few ones in the oracle, versus in the no instance we have very few ones. Because of this last fact, in the yes instance there are in fact lots of ones in the oracle, and you can tell that apart from the no instance, because in the no instance there are few ones, and the yes instance there are you know, lots of ones. I mean, what we can only hope for that is that you can't tell apart very few ones and very few ones. Okay, so what this means is that if we are going to hope to separate QMA and QCMA with this kind of construction, we are going to need a relation, unlike hidden matching, that is kind of sparse. So what we are going to use for this is the Yamakawa-Zhandry problem that I mentioned earlier. Oh, by the way, before I continue, does anyone have any questions? Oh, how am I doing for time? Okay. Okay, the Yamakawa-Zhandry problem is like this. So there will be a fixed linear code in 0, 1 to the mn, and there will be a function f from n cross 0, 1 to the m to 0, 1. The Yamakawa-Zhandry problem looks a little bit complicated. So it's going to be like this. R of f is going to consist of pairs xu, where x is a string in 0, 1 to the n, and u is a string in 0, 1 to the mn. And the requirement is that u must be a code word of the fixed code C that we have. And also for every I, f I comma ui should evaluate to xi. I know this looks kind of complicated, but so this was used by Yamakawa-Zhandry basically to separate not BQP and BPP, but quantum and classical polynomial time algorithms relative to a random oracle. Basically, before that, nobody believed that quantum algorithms could have any advantage over classical for with respect to a uniformly random oracle. So Yamakawa and Zhandry showed that when this code C is large enough, and it also has good list decodability parameters, then for every x there is a quantum algorithm A that can find an xu in R of f for a uniformly random f with only polynomially many queries to f. And but on the other hand, the classical lower bound is that no algorithm can find with only polynomially many classical queries can find xu in R of f for a uniformly random f. So after Yamakawa and Zhandry's result, Liu in 2023 observed that the quantum algorithm that Yamakawa and Zhandry provided, the queries it makes to the oracle don't actually depend on x, and the queries are also not adaptive. So yeah, I mean, it doesn't need to decide where to query next depending on the query answer and so on. So this means R of f can actually be solved with no queries to the oracle and a quantum advice state. So whatever the quantum algorithm was, whatever quantum state the quantum algorithm of Yamakawa and Zhandry was preparing by making queries to the oracle, since it doesn't depend on the input x anyway, you might as well provide it to as an advice, and the problem can be solved with this advice. The advice state basically looks like this. It's a superposition over all ui, f I comma ui, and you need to give this for every I basically. And Liu also showed that R of f can't be solved with classical advice. It basically kind of just follows from Yamakawa and Zhandry's result. Okay, so I said we are going to use the YZ problem for our QMA versus QCMA separation, is going to be the oracle I described, this O of f comma E, with the relation R of f that we are going to use being the Yamakawa-Zhandry problem. Okay. Now, a thing to observe is that O of f comma empty set is a verification oracle for R of f. It's because if you query x comma u to the O of f empty set oracle, it gives you 1 if xu is in R of f and gives you 0 otherwise. Now, this means if we can solve the YZ problem with access to this verification oracle and classical advice, then we can also distinguish O of f comma empty set from O of f comma E for a large E, which is the two oracles that we do have to distinguish for QMA versus QCMA. Okay. So, what we really need to show is that, what we need to show is kind of, but not exactly, that the Yamakawa-Zhandry problem should remain hard with classical advice and a quantum verification oracle. So, from the result of Liu, we know that this problem is hard with only classical advice. From the result of Lee, Liu, Pelecanos and Yamakawa, we know that it is hard with classical advice and a classical verification oracle. We also know that it is hard with a quantum verification oracle actually, with from the result of LLPY. So, but this is only with a quantum verification oracle and not with quantum verification oracle and classical advice. But on the other hand, from the result of Yamakawa and Zhandry themselves, we know that it is in fact easy with quantum access to an oracle for f itself, not a verification oracle for R of f. So this means that if it has to be hard with access to a classical advice and quantum verification oracle for R of f, then a quantum verification oracle should be much weaker than a quantum oracle for f itself with classical advice. Okay, so that's what we need to show for our QCMA lower bound. Okay, so yeah, we are in the setting of the Yamakawa-Zhandry problem with the quantum verification oracle and classical advice. What we do is we decompose the classical advice into a partial assignment on f basically. It's a little bit like in general, a classical advice can give you and some arbitrary information depending on all bits of f. By a partial assignment on f, I mean that some bits of f are fixed and the rest of the bits of f are uniform actually. This is in general, classical advice can be anything, so this is not in general true, but we can use a result of Goose, Pitasi and Watson, who showed how to decompose high mean entropy distributions into dense distributions. After getting the classical advice depending on f, our distribution on f is going to be high mean entropy. This is just because there are lots of f's and the classical advice is small, though. So, even conditioning on the classical advice, this distribution is going to have high mean entropy. And then we use Goose, Pitasi, Watson's result, and we get this decomposition into dense distributions. So, a dense distribution is fixed on some bits, and on some other bits it has like high mean entropy in a way that lets us say it's kind of uniform, and that's good enough for our purposes. So, yeah, so we are just going to kind of fix a partial assignment depending on the classical advice. Now, what can a verification oracle for R of f tell us? Okay, so I said R of f is a TFNP relation, and that means that for every XU pair that is in R of f, if you know that it is in R of f by querying the oracle, then there is a partial assignment certifying this. So, if you query XU to the oracle and get an answer 1, you can know in fact n bits of f. So, consider some XU pairs for the relation and some partial assignments P's, XI UI pairs and some PIs certifying these. So, initially when we had the uniform distribution on f, all these partial assignments, since they are n bits, they were very unlikely. They had probability only to the minus n. But now we start with a partial assignment q on f due to the classical advice. Now, suppose this q and the PIs are such that the q fixes almost all bits of the PIs except one bit, and suppose these bits also do not overlap. That means after fixing q, the partial assignments P's, their probabilities increase by a lot. I mean, they were previously 2 to the minus n, and now they're half. Now, this can be kind of dangerous for us because, okay, let's see what a quantum algorithm can do with this. So in round 0 of the algorithm, you start with the classical advice. You haven't made any queries yet. Now, due to this classical advice, like I said, some other partial assignments become likely. So in the first round of the algorithm, you can potentially query one of these, the XU pairs corresponding to one of these PIs, and then you can potentially learn PI. So in one of these paths, if you query this XIUI, you will have learned Q, and you will also have learned the extra bit corresponding to PI. Now, after you have done this, you have the partial assignment Q union PI, and because of this, some more partial assignments become likely. And in the second round, assuming you only make one query in the second round, we are in general going to make polynomially many queries, but let's consider one query for now. So in the second round, you have some more partial assignments that have become probability half say. You can query one of these and get another bigger partial assignment and so on. Now, I've been talking about this like it's, the quantum algorithm actually has to traverse one of the paths in this graph or something, but it's a quantum algorithm. It doesn't have to do that. It can query all of these partial assignments in superposition. Now, remember what the advice state for that would help us solve the Yamakawa-Zhandry problem actually was. Is this state? It's like superposition over all positions, and the value of the function f at that position. If this graph was bad, like structured in a badly enough way such that you can get all the bits of f in superposition like this, then that's very bad, because that is the advice state that will help us solve the problem. But fortunately, we are able to show that the Yamakawa-Zhandry problem has this property that we call slipperiness. This basically follows from the fact that the code used in the Yamakawa-Zhandry problem has like good list decodability parameters. So because of this, we can show that if we fix some partial assignment Q, then the partial assignments Pi that become likely because of this, like the union over them is like not too large. So that means at least in bounded rounds, the algorithm cannot prepare this state, this advice state sort of thing, and therefore it cannot solve the problem. Okay, yeah. Oh, sorry, yeah. Yeah, okay, yeah, that's basically almost the end of my talk. I'm not going to go into technical details. We basically show that, the Yamakawa-Zhandry problem has slipperiness. And that's how we can show the lower bound. But on the other hand, the slipperiness parameters are not good enough. Like we have for a fixed partial assignments Q, the sum union over PIs is kind of small, but it's not really small. What we actually need is some R of f for which which is highly slippery. So suppose Q is of some size Sn, then this union over PIs needs to be to the small o of log of Sn, so like much smaller. And also obviously R of f needs to be solvable with quantum advice. If such a relation exists, and we conjectured that it does, then by our techniques this would lead to a full oracle separation between QMA and QCMA. And yeah, whether or not this conjecture is true, we leave as an open question. There are also maybe some other open questions, like I said, all oracle separations between QMA and QCMA lead also to oracle separations between BQP by Q poly and BQP by poly. It's probably also true of our oracle separation, but we didn't bother proving it. But on the other hand, it is kind of annoying that this seems to always be, there seem to be related oracles that separate these two classes, but there's no black box reduction or anything. You have to do a new proof each time. So it would be nice if there's a black box reduction from a QMA QCMA separation to a BQP by Q poly versus BQP by poly separation in either direction. The second open question I have is that can we separate QMA and QCMA in communication complexity? So yeah, this question is still open in communication complexity. Query separation of QMA and QCMA has implications for relativizing proofs. Communication complexity separation would have implications for proofs, algebraizing proofs basically. That's I don't want to get into detail about what algebraizing proofs are, but that's another barrier. And yeah, okay, that's all the open questions I have, and that's the end of my talk. Yeah, thanks.
Thank you very much for the talk. I guess we have time for at most one quick question, if we have any. Okay, if there are no questions. Sorry, Joseph, could you go? Okay.
The first slide, they conjectured that QMA and QCMA are equal in the Turing machine model. I'm not sure if people believe that now.